As an architectural technologist, I am deeply passionate about this profession. I've spent over 20 years in it and done loads and loads of things around the world. This is one example of a project that I was involved in Shanghai. I've been to Australia, all over Asia, Americas, Bahamas, places like that. I think I've done projects in about 60 countries all over the world. Any given day, I could be talking to the CEOs of large organizations, presenting them with technical designs that we're coming up with. And then later on in the day, I'm talking to the guy sweeping up the rubbish on site, telling him to wear his hard hat and make sure that he's safety conscious and things like that. So everything in between, all that. I think my passion for what I do is largely helped by the company I work for, Gensler. The philosophy that the company operates under is we want to make the world a better place to live, work, and play through the power of design. And our company thinks of design under two different words that also begin with D. One is still design, but also delivery of that design. Design without proper execution and delivery is just folly. It's just drawings on paper, doesn't mean anything. And the technologist is the person who delivers the project. Okay. I just want to talk, before I go to the case study, I want to talk a little bit about innovation and kind of set the scene, because without a lot of today's innovation, the building that you just saw would never have been realized at all. This kind of gives you a little bit of a kind of a timeline over the last 100 years or so of great innovations throughout time, and I think what you'll probably notice that, and I think we all instinctively agree with that, over time, the rate of innovation impacting us and propelling us forward is increasing exponentially. Interestingly, if you correlate that to world's population, I know that was talked about kind of locally here earlier on today, in 1950, in the 1900s, we were looking at a global population of about 1.2 billion people. 2000, we're about 6 billion people. 2050, it's expected to be 9 billion people. So maybe the rate of innovation is kind of helped by the fact that there's actually more of us here on the planet as well. So that's something to think about. If I look back, again, 100 years ago in a little bit more detail, my wife's actually in Finland at the moment at the funeral of her grandmother, and she died. She was 100 years old. So she was actually around, she was born on the day where Alexander Graham Bell made his first transcontinental phone call. So that's sort of like a lifetime ago. So it's not that long ago, it's 100 years ago, but it's still within someone's kind of lifetime. Switchboard operators, a huge amount of labour was involved in this kind of human computing, making these connections together. A large labour force involved in that. The type of car that was around there, the Fiat 70 launched, and the world's tallest building at that time was the Woolworths building in America, New York. And that stayed the largest building in the world for about until the 1930s. Trimline touchstone telephones, then we're on to 1965, 50 years on from that. No longer did you have to stick your finger into and dial this thing around, you could use touchstones. The second image, it was called a mini computer at its time. Obviously now you wouldn't call it a mini computer, the size of an under-counter fridge. But that was advancements at that time. The Ford Mustang, still a design classic of that time. And the Empire State Building then took over from the Woolworth Building at 1,250 feet tall, at the largest building in the world at that time. Today, we have mobile smartphones. I don't think there's anybody who doesn't have a mobile smartphone. They do everything from still making phone calls, which we probably use your phone 5% of the time to do of making phone calls. Everything from that to what I can do over the weekend is my wife bought me a drone helicopter, and I can control my drone helicopter from that as well. It's fantastic. My tablet computing, so we're really down to huge processing power at infinitesimal kind of small sizes. This is my daughter sketching there. She just hardly even knows what it's like now to pick up a pencil, actually. You just draw with your finger. The Telsa Model S, fantastic car, great achievement in automotive technology. I don't know if you've ever sat in one. It's like sitting in a library. There's no noise whatsoever. It's a phenomenal thing. And the subject of my discussion with here today, it's not the tallest building in the world, unfortunately. It's the second tallest building in the world at 2,000, just over 2,000 feet, 632 meters, and that's just opened in October this year. So the tower, as it stands, you see on the left, so it's a trio of super tall buildings. The Jingmao Tower to the left, designed by SOM, completed in 1999. The next tower in the middle then is KPF's World Financial Center, and then the Shanghai Tower itself to the right. We were invited to bid for this job in mid-2007, along with Cesar Pelli, Foster's, Richard Rogers, KPF, SOM, and all those kind of people. We had never done a tall building before, so we said, well, why not? You know, you got to try somewhere, right? So we were conscious of trying to harmonize the site. So there was a planning application allowance at that time for a 200-meter tall building on that site. We spoke to the client and said, well, we'd like to go a little bit beyond that. And they said, well, as part of your submission, show us your thoughts. And we thought that the Jingmao Tower represented China's past. It's very closed. It was entirely made from components that came from everywhere else in the world apart from China. The center building, we felt at that time, represented China's current state of play, in that it accepted foreign financial investment within the country, so it's their financial center, World Financial Center. So we wanted to design a building that was more transparent, and acted like the bigger brother of the building, because of the trio, and we felt that China wanted to have this ambition to become more transparent as a country, and a little bit more outward thinking, and a little bit more open to the external world. So we wanted that skin of the building to be clear, and that you could see into it and into the core more than the others. The height of the building landed simply because we mapped a curve of Chinese growth during the time, and at the time we know China was growing hugely. So we landed on the 632, if you can imagine the curve of the growth of China running up there. So again, the story that we portrayed to them was powerful for that. Geometrically, the Jingmao is a four-sided building on plan that turns into an eight-sided building. The financial tower is a four-sided building that turns into a two-sided building. Ours is a three-sided building that twists as it goes up into the sky. So some stats, 121 floor levels of occupiable space, 128 stories in overall. As I said, it's over 2,000 feet tall. And 20 years ago, this piece of land, the Pengdan Peninsula, was farmland. So it kind of puts it into perspective, and not just the growth of this building itself, but the entire area. It's phenomenal growth within Shanghai. The population of Shanghai at 2000 was, it's hard to get accurate figures, it was around about 20 million, 19.7 million. And they expect by 2050 to be 50 million population in one single city. I mean, we talk about London's population being, hard to actually live in, but imagine 50 people living in one urban environment. So our view on building a vertical city was liked by the Chinese. A little bit about the stack. So on the base of the building, you've got retail and conference. So it was important for us that where our buildings meet the public realm, that we activate that in a way. So largely it's a commercial office building, as you can see. But what we didn't want was that during the weekends it became a dead space that was going to ruin the urban environment, the fabric of that. We wanted people to keep using that and have evidence of that in the urban landscape. On the zone 7 is hotel zones, 250 apartment, a 250 room hotel, and there's a serviced apartments on zone 8 above that. The observation zone takes up the last zone on top. There's actually 5 observation tower levels, and that the bottom 2 of that look outwardly across the city, and the top 3 of that are more inwardly looking at the fine-tuned damper and the technology of the building, look at the turbines that are recycling the wind coming through the building, and all the grey water recirculation and stuff like that. So we have observation levels looking out, which is important, but we also felt that we wanted to interact with the building and its sustainable achievements and its technical achievements as well, so it's inwardly looking as well. A couple of things that we'll talk to you today. Obviously, when we're designing a building that is very transparent, there's a lot of daylighting issues with that, and we'll talk a little bit about how we counteracted that with some M&E issues. The landscaping of the site, you just see it on plan there. There's a planning condition which meant that the site could only be 50% occupied, so creating this super tall structure on this site, which had a very small floor plate size to it, was posing key challenges, certainly when you come into foundations and things like that. Wind turbines, I'll talk a little bit about the sustainability approaches of it. We've had a very good discussion just now about BIM and what that means. We've used 4D BIM here, so every component that we've drawn in what we use as a Revit model to ultimately deliver our information on this is all tagged so that it can be brought to site just-in-time delivery and things like that. We also did 5D and 6D, but that's more cost planning and life cycle planning as well. LED lighting, cogeneration systems on the M&E, and I'll talk a little bit about the double skin and structures as we go through as well. So how did we come up with the form, and how did our approach to sustainability inform the actual shape and size of the building? So we found that we had 3 teams working on this when we bid for the job. One team looked at a square building, one team looked at a circular building, and one team looked at a triangular building. Now, these 3 shapes had cultural significance for the Chinese, so we felt somewhere in those shapes the ultimate design was going to come about. When we got the teams together, none of them could actually reach a final decision of a great building that we could put forward. The 3 teams got together, and what we decided to do was use the triangle as the outer skin of the building and rotate that triangle as it went up through the building. The core is the square that sits inside the building that provides all the vertical infrastructure that you need, and the circle is the looking down at the floor plates. So it's basically pancaked floor plates on top of each other on a square core, and on every 14th floor level, that pancake turns into an egg shape, and that egg shape is rotated around as the building goes up. It's so simple structure, really, but it can just look quite amazing as you rotate that through. But how we landed on the 120-degree rotation and the tapering of the building was through wind model testing and computerized model testing of this, and we found that there was huge wind load efficiencies that brought about by doing the rotation and also by doing the tapering of it as well. So we tested several in airline models usually used for testing aeroplanes. We tested a load of configurations, and this one landed us in the best twist and tapering mode. Here's a plan of one of the floors. So 120-degree rotation across 120 floors is about 1 degree per floor. You can see here the square, which, okay, it's a bit of a rectangle, but square essentially. Core in the inside, the circular floor plates, and the skin as a curved triangle that sits outside that, and that's the thing that rotates around the building. North, south, east, and west on this plan, you have the huge super columns that, again, are built tapering as well, so they taper up following the taper of the building, and just radiating out of the corners. You have the smaller super columns on that as well. We have there's 106 elevators in this building. And what they do is each of the zones, so we've got 9 zones, so you go into the building, and 30,000 people enter this building every day. You take a double-decker elevator up to your zone, and then you walk onto that amenity level, which is the egg floor plate of that zone, and you walk around to your local lifts, and you take the local lifts within the district that you're on in each of those zones. And that's how you get around the building. This is a photograph of one of the winds testing. So yes, so what we found through and how we landed on the rotation and the tapering, we were able to reduce wind loads on the building by 24%. That's based on if you just did a standard rectangular or square kind of structure. And that resulted in 32% reduction in the steelwork required to support that building, which had a $58 million saving to the client. So we were able to save that much money and come up with a beautiful building and save money for the client and use less material to do it. Here's some of the structure in 3 dimensions. So the cores in red, shear walls. We've got steel riggers, connect that to the super columns, and then you've got a super belt truss on the green that rotates around that at the top and bottom zones of each of the zones. So the belt truss at the top is going to support the glazing, curtain walling that comes down to support that outer skin that we talked about as well. And you can see the egg-shaped floor plates as they come about at each top and bottom of each of the zones as well. So this guy kind of just helps maybe illustrate it for you a little bit better how that outer skin sits outside that circular inner skin. So the outer skin is a single layer glazing, and then the inner circular one is a double glazed layer as well. Okay. So I'll talk about that. I think in my previous version of this, I actually showed the foundations of that. It was it's a 6 meter deep mat foundation. It's actually took 62 days for 420 wagons to pour, continuous pour of the mat foundation. It's the longest pour and the largest volume pour in Asia ever made. It's absolutely phenomenal. You can see each of the zones of the section. If I maybe point, I can't walk away from the microphone, but at the ends of each of the zones, maybe there's a better, I think there's a better image. Yeah, this one. So the reason why we had 14 floors for each of the zones, we were limited in Chinese regulation, whereby in China we developed with the fire officer, so there's, codes and regulations exist, but for something like this, you have to kind of rethink that a little bit, right? So we talked to the fire officers in China, and we talked to them about fire escape on a building. Now, if this building was undergoing on typical regulations, it would take about 2 hours to evacuate the building, at which point maybe the building's already fallen down, or certainly you'd have some fatalities. What we discussed with them is the highest level that we could go was 14 floors and provide a refuge floor for the occupants of the building. So it's on the basis that they can use elevators to evacuate the building. Okay, so we have to make those elevators fireproof. Okay, so we can make that happen. That's easy. And what happens is on the upper, you see the 2 floors in the middle. The lower one is the mechanical floor that serves the lower stack of the lower 14 floors of that section. The upper one that's empty there, that's the refuge floor, where all of the people in the 14 floors above that evacuate into, in the case of a fire, and they're evacuated from that floor with the double-decker elevators. And we can get 30,000 people out of this building in 27 minutes. That's pretty good going, I think. Obviously, with an atrium size in every zone, again, you're talking about 14 floors. You've got a single glazed facade. There's a heat gain in that. How do you deal with that? So, well, we only had occupiable space at the lower part of these are the amenity, what we call the amenity floors of each zone. So we had localized cooling in that space. So that's easy to do, but let the rest of the heat go up through the building. in the wintertime, that heat is recycled into the building to provide heat for the occupants of the office floors. And in the summertime condition, it actually vents out through the building at that mechanical floor at the top of the zone, and it goes out into the open. As you can see there, this is the summer operation, and in the winter operation as well. I think we did thousands of hours of CFD modeling on this thing. I think you talk about computer programs and the reliance on computer programs when you're dealing with something that kind of hasn't really been done before. We find ourselves having to step away and go, as a professional, given years of experience, is this instinctively right what we're doing? And computers can tell you a lot of stuff and they can do all that, but you really have to have that kind of the gray-haired kind of attitude to it, and actually say, are we confident that's going to be the right thing? The computers can say yes, but computers are sometimes not always right. There's just a photograph I took. The site's still not finished at that stage. There's some panels missing. You can see up into the soffit up above. And again, the panelized system on the glass. There's 30,000 different types of glass size in this project. No floor has more than 3 glass sizes the same. I think in the days before the computer technology that we have, I don't think we would have been able to do this project to the level of detail that we're doing. I mean, the difference between the glazing panels is 0.2 of a millimeter in some points, right? So you're being a bit anal about it, but it is still a bit different. And again, each of these is tagged through the Revit model, and it arrives on time on site, just in time for the crane to get into the staging area, and this crane stages it up. It's like a carefully orchestrated operation. It's really, really phenomenal. Everything down to, we had to involve ourselves down into everything, but the system schematics and everything had to be in Chinese and English, which sometimes was a bit of a pain in the ass, but it just had to be done. Everything had to be redundancy. This is just one view of a corner of a core, so it's N+2, so you had 2 building equipment rooms. This is just one view. There's another one at the opposite end of the corner. TR is providing another level of redundancy each side, so it's another N+2 redundancy across each of the cores for critical infrastructure in the building. The wind turbines that I talked about, so you can see the 3 levels of wind turbines on the right-hand side image there. There was two good things about this. One is it allowed us to puncture into the building, so again, reducing the wind load on that building, so again, having impact on the structure and what we talked about earlier, but also we're capturing the energy of what was found is that we had a kind of pretty average 6 meters per second wind speed at that height, and it was between 5 and 7, but they said it was around about 6. So we were able to fine-tune our wind turbines to be able to counter to that as optimum energy output based on the wind speed coming in. Anyway. So behind that is the 3 observation towers that existed. I talked about it a little bit earlier, and behind that then is the central fine-tuned damper within that stops the building from swaying. The glazing itself, as I said, so the external skin is made up of 2 10-millimeter layers of low iron e-coated glazing, and they're laminated together. I've been told by the producer of the glasses that any human being could run full force at the glass and they would not break the glass. I don't believe we've ran that test, but it's fritted on the edges as well, because again, we're doing that very transparent building. We want people to see into it. All the other buildings in China, because of the sunshine, they're very opaque and very closed. But again, we had to do that. So we just did minimal kind of fritting on the building, glazing. And inside, well, you can't see maybe on this one, you can see the inside is just a standard double glaze system internally on the circular core as it goes up. LED lighting is incorporated to the whole of the facade. Actually, the wind turbines on the top power the external buildings LED lighting. I don't know if you've ever been to Shanghai on a Friday night where the buildings, they just light the whole the whole thing gets lit up. It's like a fireworks display. Without the fireworks, it's just in light. The whole facade is covered in LED lights. So it was very important that we were able to use a sustainable energy to power that, because I think instinctively as designers we felt really bad that you'd have to spend all that money just on lighting, on a light show basically. Our advancement in technology, I know we've talked a little bit earlier about BIM. We use various tools in support of collaborating with our other design team members. BIM for me is a process. It's not a model. It's a facility to create dialogue between people with a single ambition, which is to be able to, well, for me personally, make sure that my building stands up. For my design partners, working on things to make the building really look beautiful, so you don't get clashes on site and you have to make concessions and things like that. So coordination of that tool, whatever tool you use, is vitally important. But for me, BIM is really you have to bring the client in on this discussion, because really it's about the life cycle of the whole building, not just how you get it built and designed. It's about how that building is run efficiently. It's about that building can minimize the cost for the client to operate, be it a homeowner or be it a big tall skyscraper and stuff like that. So there's some extracts that talk about how detailed that building is. It's not only sloping, tapering, it's curving, it's things like that. It's where do you put the fenestration, what levels there are. It's a highly detailed process to undergo. Just a section I thought you might like. I thought technologists might get a kick out of seeing a detail. I don't know. It's the problem with presenting a case study like this over a relatively short space of time is there's so many details to think about. I can't show you hardly any of them. They only scratch the surface, really, and things like that. But we're doing things for the first time, and we're trying to make them into standardized components, or you'll go push through the design barrier and get to a stage where you can use standardized components to realize that design. That was our philosophy. And by doing that, we were able to use 100% all locally sourced, locally in China, sourced material, right? I know China's a big country, so it's not that local, but at least it was all sourced and local, which again, we felt the Jingmao Tower did not do, because nothing was sourced in China. And again, what we wanted to do was represent the future of China, which was, they are a country in their own right, and they're progressing as they are. Here's one of the panels going in. I was at a lecture, I did this in America not so long ago. We talked about, had a different thing about how the cranes were up on the building. Actually, the contractor, through clash detection on the cranes, we had 4 cranes on all sides of the cores going up, and most of the other all of the other contractors said that they can only get 3 without doing collision on the cranes as they were going to go through the thing. This contractor came in and said they developed a collision detection program which allowed them to put the other 4th crane on the other 4th face, and that reduced the program by 18 months. And they were the successful contractor on the project. But that's it. I just wanted to leave you with a personal statement from me, kind of. I've been doing this for 20 years as a technologist. Perhaps I don't work on mortar drippings on cavity walls and things like that so much, but I am aware of it, right? And it's a bit like a shout out to the industry. I think you're all technologists of some level, maybe architects, or there's a chartered surveyor here, I think, or something. It's the best. I could not think of a better job to do. I think my life has been, so I'm getting a bit emotional about it, but I shouldn't be, but I have gone all around the world doing what I do. I'm not particularly intelligent, I'm just really good at what I do. And to students out there or whatever, you go for it. This is the best job in the world. Thank you.